So different ways we could go about doing this. Which side do y'all think is the more complicated side? Yeah, I think the left side is too, because, I mean, neither side is just pretty. But at least on the right side, our angle is a single letter. On the left side, we have two different letters. Several different ways we could go about doing this one. We could use our product to sum identity. Another approach, we have a sum and difference identity for sine. We could take these and change it to using our sum and difference identities. Which way you want to do it? Doesn't matter. You want to use the product to sum, or you want to use the sum and difference identity? Sum and difference. All right. I don't know where that's going to go. We'll try it and see what happens. So remember, if we have sine of an angle plus another angle, we can change that to sine of the first angle, cosine of the second, plus cosine of the first, sine of the second. Sound familiar? I think we had that one on a quiz yesterday, maybe. Then, speaking of, y'all might want to study a little bit more on those identities. Most of y'all probably know what y'all got right or wrong on that quiz. The average for the class just wasn't so hot. Some people got them all, I think, but when I say some people, that might have been one person. But
putting that out there.
Yeah.
What?
I like the way he said it. Probably me.
No.
All right, so for the second one, if we have a minus here, it's still sine the first angle, cosine the second, cosine the first, sine the second, but it's got a minus in the middle. Now that's all good and well. Now we need to multiply that out. So if we have two terms times two terms, we have to distribute, or some people use that F word. Not that F word, the other F word. Full. So we multiply those out. I'm not trying to be ugly. I'm just trying to... Yeah, I know how y'all are. No. We multiply those two. We have sine alpha cosine beta times sine alpha cosine beta. So sine alpha times sine alpha is sine squared alpha. Cosine beta times cosine beta is cosine squared beta. If we multiply these together, positive times negative is negative. Let's see. None of our angles and things match. We have sine alpha, but we have cosine alpha and sine beta. Cosine beta, but we don't have a cosine beta. So we just have to write each of those factors out. Sine alpha, cosine beta, cosine alpha, sine beta. We don't have anything squared there, because notice none of those are the same. So then we need to distribute here. Same thing. Cosine alpha, sine beta, cosine beta. Positive times positive is positive. Cosine alpha, sine beta, sine alpha, cosine beta. So all of that's multiplied together. Then we have that product. Positive times negative is negative. This time we do have a cosine alpha times cosine alpha, so that's cosine squared alpha. Sine beta times sine beta, that's sine squared beta. So that's fun to multiply out, or not. But we completely distributed all of those multiplied common factors together. What do you notice about the two middle terms? They cancel out. They're opposites. Now, as they're written, they don't look exactly the same, but they are. If we change the order, we got a sine alpha in both times the cosine beta times the cosine alpha times the sine beta. We have 1 here minus 1 here. So those are opposites. Those cancel. So we got a sine squared alpha cosine squared beta minus sine squared beta cosine squared alpha. Is that right? Make sure we didn't miss anything. Yeah, cosine sine squared alpha cosine squared beta cosine squared alpha sine squared beta. Are there any are there common factors between those two? No common factors. Let me bring down the right side real quickly. Obviously, those are not the same right now, are they? So, just looking at it, nothing looks really good on either side. But notice both sides are differences of squares. We have a square minus a square minus a square. I don't know where this is going to go, but let's just see what happens if we factor the left side out as a difference of squares. This is sine alpha cosine beta, this being squared. This is sine beta cosine alpha, that's being squared. Same terms with a plus in the middle. Nothing really looks like it's going to go away or get any better. We probably could do something eventually there to make this that. Couple things we could do. Let's do this. That made that worse. Notice on the right side, everything is which function? Sine. Is everything sines on the left side? No. So, let's take a little aside. What's sine squared plus cosine squared? 1. So if we want to get rid of the cosine squareds, we can make a substitution. If we solve this for cosine squared, cosine squared is the same thing as 1 minus sine squared. So the right side is more simple, and it only has sines in it. So let's see what happens if we get rid of these cosines by making a substitution. So where we have cosine squared, let's change that to 1 minus sine squared of that angle. Where we have a cosine square, let's change it to 1 minus sine squared of that angle. Sine squared times 1 is sine squared alpha. Sine squared times minus sine squared, those are different angles, so we do have to keep those separate. That's sine squared alpha times sine squared beta. When we distribute here, minus sine squared beta times 1 is minus sine squared beta. Minus times minus is a positive. That's sine squared beta times sine squared alpha. Notice those are the same, so those cancel. And what we're left with is the same as what we have on the other side. So the suggestion that you made was, okay, it got us to where we needed to go. That was probably an easier way to have done that one. Let's just go back, how to work through that, and see if we would have been better off using our product to sum identity. We made accurate substitutions. We changed that to something it was equivalent to. We took that, changed it to something it was equivalent to. We distributed it accurately. We canceled out some terms accurately. We still had a mess. We recognize, hey, we only want sines, so we need to do something to get rid of those cosines. Anytime you have a sine squared or a cosine squared and you need to get rid of it, keep in mind we have an identity that we can do that with. Sine squared plus cosine squared is 1, so if we want to get rid of sine squared, solve it for sine squared and replace it with the other side. If we have a cosine squared, solve it for cosine squared, replace it with the other side. So that will work. Let's go back and do this with the other suggestion that I had originally made. Notice we have a product on the left side, but we have a difference on the right side. So we have an identity. Actually, we have two new sets of identities. We have a product to sum, and then I believe it was on the next page, we had a sum or difference to a product. So sum or difference to a product. Now, we probably don't want to use this one because we have sine squared minus sine squared. This isn't sine squared minus sine squared. This is sine to the first power minus sine to the first power. So we probably can't use this to change the right side, but we do have a product of two sines. Here, notice we have an identity for a product of two sines. So we're going to call this angle X, this angle Y. So this identity says take half of cosine of the angles subtracted. So subtract those angles, alpha plus beta minus alpha minus beta. Then minus cosine of the angles added together. So minus cosine of those angles added together. Well, just real quickly, if we add those angles together, alpha plus beta plus alpha minus beta, the betas cancel, that gives us two alphas. And let's go in and clean this up. If we subtract those, alpha plus beta minus alpha minus beta, that's alpha plus beta minus alpha plus beta. So that's 2 beta. So cosine 2 beta minus cosine 2 alpha. Do we have cosines on the other side? We don't. We also don't have 2 alphas or 2 betas on the other side as our angle. We have 1 alpha and 1 beta. So anytime we have cosine of twice an angle, keep in mind that's a double angle identity. We have cosine squared minus sine squared. We have 2 cosine squared minus 1, and we have 1 minus 2 sine squared. So if I have cosine of twice an angle, but I don't want to have twice an angle in my answer, then I can use this identity to reduce it from cosine of twice an angle to something of my angle, or one of my angles. This is called a double angle identity. It's also sometimes referred to as an angle reducing formula. We reduce our angle from 2x to 1x. Now, on the right side, again, do we have cosines on the right side? We don't have any cosines on the right side. So when I pick which one of these to use to replace with, I'm probably going to pick one that doesn't have any cosines in it. That one doesn't have cosines. So let's change the first one to 1 minus 2 sine squared. Instead of 2 beta, it's 1 beta. Instead of 2x becomes 1x. Minus, notice this minus applies to all of that. So minus, if we change that to 1 minus 2 sine squared, it's 1 minus 2 sine squared alpha. So this is 1/2 times 1 minus 2 sine squared beta minus 1 plus 2 sine squared alpha. Notice 1 minus 1 is 0. This term is positive, so let's call that 2 sine squared alpha minus 2 sine squared beta. If we distribute the 1/2, half of 2 is 1. Half of 2 is 1. And that's exactly what we started with on the right side. So notice we did 2 completely different things, but both of them we were able to simplify it down to having the same thing on both sides, which proves that it's an identity. There are some that are much simpler than that. Some are a little bit harder than that. It just kind of varies a little. Let's look at 21. 21, we have 1 plus cosine squared over sine squared equals 2 cosecant squared minus 1. Let's see. On the right side, we have 2 different terms. On the left side, we just have 1 fraction. But we can take that fraction and break it up into 2 terms. What can I do to this fraction so that I have 2 different fractions or 2 different terms? Yeah. So use our common denominator and do 1 over the denominator and then cosine squared over the denominator. Now I'm going to be just a little careful here. I would be fine with you skipping this step. But notice 1 over sine squared, we could write 1 over sine all squared. Notice if we have a fraction squared, it's the numerator squared over the denominator squared. So that's 1 squared over sine squared. Same thing for the second fraction. Cosine squared over sine squared, we could call that cosine over sine all squared. What's 1 over sine? The same thing as 1 over sine is cosecant. That says to square cosecant. What's cosine over sine the same thing as? Cotangent. That says to square it. Still don't look the same. Also, one thing to be careful with, we mentioned yesterday, make sure you don't take something from one side and move it to the other. It's just not a good practice during proofs. That would actually make this a lot easier. It's not what we want to do. Earlier we said, okay, if we've got cosine squared or sine squareds, think of the Pythagorean identity. Same thing here. Remember 1 plus cotangent squared is cosecant squared. 1 plus tangent squared is secant squared. Now, if we're not doing a proof, if we have something that we already know is an identity, it is okay to move things from one side to the other. But if we have something that is not an identity, that's when we don't want to move things around. So, our problem has some cosecant squareds and some cotangent squareds. There's a variety of things we could do here. We could take this cotangent and say, hey, the other side doesn't have any cotangents. So let's change this cotangent squared into something that doesn't have cotangent, that just has cosecant in it. Or we could change this cosecant into something that has cotangents in it. Or we could change this 1. We could actually solve this for 1 and say, well, what's 1 the same thing as in terms of cosecants and cotangents? Well, let's do it. Any of those will work. Let's change this to cosecants. So if we take this identity and solve it for cotangent squared, what's cotangent squared the same thing as? Cosecant squared x minus 1. Subtract 1 from both sides. Cotangent squared is cosecant squared x minus 1. So we already have a cosecant squared x. We're changing this to another cosecant squared x minus 1. Cosecant squared, another cosecant squared makes 2 cosecant squareds, and then we have a minus 1. Same thing we had on the other side. Not the only way we could have done that. That's just one way. Another alternative, one thing we mentioned yesterday was sometimes it's good to change everything into sines and cosines. We could have changed cosecant. What is cosecant in terms of sines and cosines? See, cosecant is the reciprocal of which one? Sine, we could have changed that to 1 over sine squared, so 1 over sine squared. So that would have given us 2 over sine squared. We could have gotten a common denominator, written out as a single fraction. That would have given us some sine squares on top. We could have changed that into cosine squares so that they would have matched. So we could have done it by changing to cosine squares and sine squares. The biggest thing, though, is to pick a side, try to simplify it as far as you can, try to make it look like the other. If you can't simplify one side anymore, try to take the other and simplify it until you make it look the same. But one thing we'll always want to do, we'll always want to pay attention to the angles on each side. If we have like 2 x's on one side but 1 x is on the other side, that's going to be a clue that, hey, we're going to have some identity that changes from like 2 x's down to 1 x's, or 1 x's up to 2 x's. So also, if we've got signs on one side but we don't have any signs on the other, we might need to use an identity that changes signs into something else. So there's a lot of flexibility here. It involves a lot of critical thinking. Let's look at 19. All right, which side are you going to start out simplifying? Left side. What should we, any suggestions on what to do first? Distribute. Let's get rid of this parenthesis by distributing. Tangent times tangent is tangent squared. Tangent times cotangent. Actually, several things we can do here. What is the reciprocal of cotangent? Tangent. Remember, cotangent and tangent are reciprocals, so we could call cotangent 1 over tangent. Well, what is tangent times 1 over tangent? 1. So that gives us tangent squared theta plus 1. Anytime we see something squared and a 1, we need to keep in mind our Pythagorean identities, which are sine squared plus cosine squared equals 1. 1 plus cotangent squared equals cosecant squared, or tangent squared plus 1 equals secant squared. So what's tangent squared plus 1 the same thing as? Secant squared. So we can replace it with secant squared. And what's our angle? Theta. Well, that's what we had on the other side. It'd be nice if they're all that simple. Some are, some aren't. Let's do 23, and we'll call it a day. 1 plus sine x over 1 minus sine x plus sine x minus 1 over 1 plus sine x equals 4 secant x tangent x. So the left side, I'd say that's probably messier. What do we need? What should we do to that left side? Common denominator. What would that common denominator be? Right. That whole thing is one factor. That whole thing is one factor. The product of those on bottom. So the first fraction needs a 1 plus sine x on top and bottom. If I multiply by a 1 plus sine x on bottom, I have to do that on top. Be careful that you don't say, well, I've already got a 1 plus sine x. If we multiply by a new 1 plus sine x on bottom, we have to multiply by a new one on top. On the second one, it needs a 1 minus sine x on bottom. So if I multiply by a new 1 minus sine x on bottom, we have to do the same thing on top. So that gives us 1 plus sine x times 1 minus sine x as our common denominator. Real quickly, if we distribute this, we're going to have 1 times sine x, another sine x, so 2 sine x's. Sine times sine will make that sine squared. The second fraction, sine x times 1, is sine. Sine x times minus sine x is minus sine squared x. Minus 1 times 1 is minus 1. Minus 1 times minus x. That almost came out bad. These sines and x's and secant x's. I wasn't going to say this yesterday, but if I ever start writing secant x and I leave the x out, I'm not trying to be dirty. It's just, it happens. Well, it is what it is. It's okay, I'm married. So, all right. So if we put these together, they both have that on bottom. We have a 1 plus a minus 1. What's going to happen to those? Those cancel. We have a sine squared minus sine squared, so those cancel. We have a 2 sine x, another sine x, so 3 sine x, another one, so 4 sine x. Let's multiply that denominator out for kicks. If we multiply that out, we get 1 minus sine x plus sine x, so the sine x's cancel. Sine times sine, so minus sine squared. What did I say earlier? If we have sine squareds and 1s or cosine squareds and 1s, we need to think of Pythagorean identities. Notice if we subtract sine squared from both sides, what's sine 1 minus sine squared the same thing as? 1 minus sine squared, that's just cosine squared. Now, if we're clever, we can take this and make it look like the right side. If you see that, good. Let's do that. If you don't see that, though, it might be easier for a lot of us to take the right side and change it to the left side. What is secant in terms of sine and cosine? 1 over cosine. What is tangent in terms of sine and cosines? Sine over cosine. So if we multiply those three out, we have 4 times 1 times sine, so 4 sine on top. 1 times cosine, so cosine squared on bottom. So it doesn't matter what we end up with as long as both sides are the same thing. So if you haven't worked through a lot of those, I mean, there'll be several of these on the test, so I would highly encourage you, even though there's not my math lab assignment for 7.3, I would work through these out of the book